Mga Mix, welcome to Winnie Luna Nahiel Eduk channel on mathematics and other related topics. For this video, our discussion will focus on the measure of central tendency. Measure of central tendency. Okay, let us have some definitions in this topic. First, let's have statistics. Is a branch of science which deals with the collection, presentation, analysis, and interpretation of quantitative data. So here we have collection, presentation, analysis, and interpretation of quantitative data. Then the branches of statistics, we have descriptive statistics is a method of concerned with collecting, describing, and analyzing a set of data without drawing conclusions or inferences about a large group. So we simply or merely do a descriptive statistics. Then we have inferential statistics is a branch of statistics concerned with the analysis of a subset of data leading to predictions or inferences about the entire set of data. So in here, we have to use a sample of a population to make a prediction or a conclusion about the population. So using the sample to make a prediction or an inference about the characteristics or the attributes of the population where that sample was taken. Statistics. Then we have here frequency distribution. Frequency distribution is a tabular arrangement of data into appropriate categories, showing the number of observations in each category or group. There are two major advantages. It encompasses the size of the table and it makes the data more interpretive. Then let's have the parts of frequency table. We have class limit. What is this about? It is the grouping or categories defined by the lower and the upper limit. So LL here stands for the lower limit, UL stands for the upper limit. So for example here, 10, the lower limit, then 14 is the upper limit of this category. Then the second category, we have 15 to 19, 20 to 24. Now, lower class limit represents the smallest number in each group. So, for this 10 to 14, the lower class limit is 10. Then, the upper class limit represents the highest number in each group. So, for 10 to 14, the upper class limit is 14. Then, the class size is the width of each class intervals. Do not be confused why I have written here CI instead of CS because class size refers to the class interval. So here, the lower limit, the upper limit, 10 to 14, the class size here can be counted from the lower limit to the upper limit. Same also for 15 to 19, 20 to 24. The class size here or the class interval in this score distribution is 5. So 10, 11, 12, 13, 14. So that's the class size or the class interval here is 5. Now, the third part of a frequency table is the class boundaries. These are the numbers used to separate each category in the frequency distribution, but without gaps to create gaps created by the class limits. The scores of the students are discrete. So you have to add 0.5 to the upper limit to get the upper class boundary and subtract 0.5 to the lower limit to get the lower class boundary in each group or category. For example, here, 10 to 14, the lower class boundary is 9.5 because this 10 is subtracted by 0.5. Then the upper limit, which is 14, is added by 0.5, so it becomes 14.5. So this is the upper class boundary. So the same also for 15 to 19, then 20 to 24. Then we have the class marks. This is a part of the frequency table. Class marks. These are the midpoint of the lower and the upper class limits. So you have class mark represented by x sub m equals lower limit plus the upper limit divided by 2. So in this illustration, the lower limit is 10, the upper limit is 14. You take the sum, 10 plus 14, that is 24, divided by 2, so that is 12. So this is the class mark or the midpoint. So for 15 to 19, the class mark is 17. For 20 to 24, the class mark is 22. Now, these are the steps in constructing frequency distribution. First, compute the value of the range. Range is the difference between the highest score and the lowest score. So range is equal to highest score minus lowest score. Then determine the class size. The class size is the quotient when you divide the range by the desired number of classes or categories. The desired numbers of classes are usually 5, 10, or 15. They depend in the number of scores in the distribution. If the desired number of classes is not defined, so class interval or the class size is equal to R over desired number of classes, or class interval equals R over K. Now, the range can be easily obtained or determined because all you have to do is find the highest score and the lowest score. But the value of k, you have to do some calculation. Our k here is 1 plus 3.3 times the logarithm of n, where n is the number of cases or the number of observations. Then, the second step in constructing frequency distribution, set up the class limits of each class or category. Each class defined by lower limit and upper limit. Use the lowest score as the lower limit of the first class. Then the third step, set up the class boundaries if needed. Use the formula. This one, class interval, lower limit of the second class minus the upper limit of the first class divided by 2. Then, the fourth step is tally the scores in the appropriate classes. Then find the other parts if necessary, such as class marks, among others. Now, example here. Row score of 40 students in a 50-item mathematics quiz. Construct a frequency distribution following the steps given previously. So, you have the scores of the 40 students in a 50-item mathematics quiz. So here you have to find out the highest score and the lowest score. Now, in that given test course, the highest score is 50 and the lowest score is 15. So the difference is 35. So that is the range. Then there are 40 observations or test scores. So you can solve for the value of k. So you have 1 plus 3.3 times the logarithm of n, where n is equal to 40. So you have the logarithm of 40 is this one, 1.6020 59991. multiply that by 3.3, then the product is added by 1. So you will get 1 plus 5.28679797 So that is equal to 6.28679797 Then you can round this off to the nearest whole number. So k is equal to 6. So the class interval now, ci equals r over k. So our r, the range is 35. Our k is 6. So 35 divided by 6, that is 5.833. So you have to round it to the nearest whole number. So what we got here is 6. So the class interval is 6. Now construct the class limit starting with the lowest score as the lower limit of the first category. The last category should contain the highest score in the distribution. Each category should contain 6 as the size of the width. Count the number of scores that falls in each category. So in this particular illustration, since the lowest score is 15, so that is our lower limit of the first category. So it should have been 15 to 20. You count 15, 16, 17, 18, 19, 20. So that is 6. Then tally, there are 5, uh, 5 test scores within this class interval. Then 21 to 26, you have 9, 27 to 32, 4, 33 to 38, 10, 39 to 44, 4, 45 to 58. So you have the total number of observations, which is 40. Now find the class boundaries and class marks of the given score distribution. So we have already the class interval and the frequency. What we are going to find now, the class boundaries and the class marks. For the class boundary, remember that you have to subtract by 0.5 the lower limit and add 0.5 the upper limit. And for the class mark, you have to get the sum of the lower limit and the upper limit of a category, then divide it by 2. So for 15 to 20, that is 35 divided by 2, the class mark is 17.5. For the category 21 to 26, the sum is 47. So the class mark is 23.5. And for this category, the class boundaries for the lower class boundary, you have 20.5 because our lower limit is 21. Then for the upper class boundary, that is 26.5 because our upper limit is 26. So just repeat the process here. Then we have graphical representation of scores in frequency distribution. The scores expressed in frequency distribution can be meaningful and easier to interpret when they are graphed, and that is true. So we have to visualize our test distribution or test scores distribution. There are methods of graphing frequency distribution. You can have bar graph or histogram and frequency polygon and a smooth curve. Bar graph or histogram and frequency distribution will be discussed in the section with, while smooth curve will be discussed later in the skewness. So here, histogram consists of a set of rectangles having bases on the horizontal axis, which centers at the class marks. The base widths correspond to the class size and the height of the rectangles corresponds to the class frequencies. Histogram is best used for graphical representation of discrete data or non-continuous data. Then frequency polygon is constructed by plotting the class marks against the class frequencies. The x-axis corresponds to the class marks and the y-axis corresponds to the class frequencies. Connect the points consecutively using a straight line. frequency polygon is best used in representing continuous data such as the scores of students in a test. Now, a relative frequency distribution is very similar, except instead of reporting how many data values fall in a class, they report the fraction of data values that fall in a class. These are called relative frequencies and can be given as fractions, decimals, or percent. A cumulative frequency distribution is another variant of a frequency distribution. Here, instead of reporting how many data values fall in some class, they report how many data values are contained in either that class or any class to its left. The table below compares the values seen in the frequency distribution, a relative frequency distribution, and a cumulative frequency distribution for the following sequence of dice rules. So we have here the class limits, class boundaries, frequencies, relative frequency, cumulative frequency. Let's focus on the relative frequency and cumulative frequency. For the relative frequency, for example, in the class limit 2 to 3, so we have a frequency of 4, but the relative frequency is 2 over 15. That is because this frequency of 4 uh, has a denominator of 30. 30 because there were 30 observations in all. So 4 over 30, that can be reduced to its simplest form. We have 2 over 15. Then 6 over 30. So 6 can be divided by 6. So it becomes 1. Then 30 is again divisible by 6. So it becomes 5. So in relative frequency, we have expressed the frequency as a fractional part. So you have the frequency as the numerator and the total number of observations as your denominator. But for the cumulative frequency, it's different because you keep on adding. For example, for the class interval 2 to 3, the frequency is 4. So that's the first term or the first number in the cumulative frequency. But for the second class interval, we got 10 because under frequency 4 plus 6, that is equal to 10. And in the cumulative frequency, the third, we have 22. That is because under frequency, we have 4 plus 6, that is 10, plus 12, that is 22. So we keep on adding the frequencies in cumulative frequency. Here we have an example of a histogram. You look at this one. So for the x-axis, we have the dice rules. So that's the independent. Then the frequency depends on the dice rules. So this is our histogram. We can see the rectangles. The rectangles, the height is based on the frequency. And you can also see here for 2 to 3, the class interval of 2 to 3, we have here the class boundary of 1.5 because 2 is subtracted by 0.5 and 3 is added by 0.5. So we have this one. Okay, so that's our histogram. Next, we have frequency polygon. So here, the x-axis refers to the test scores and the y-axis for the frequency of the test scores in a given category. Describing group performance. How are we going to do this one? There are two major concepts in describing the assessed performance of the group. Measures of central tendency and measures of variability. Measures of central tendency are used to determine the average score of a group of scores, while measure of variability indicate the spread of scores in the group. Okay, so we have to be mindful of this. Measures of central tendency are used to determine the average score of a group of scores, while measures of variability indicate the spread of scores in the group. These two concepts are very important and helpful in understanding the performance of the group. So we have here the measure of central tendency. It provides a very convenient way of describing a set of scores with a single number that describe the performance of the group. It is also defined as a single value that is used to describe the center of the data. It is thought of as a typical value in a given distribution. There are three commonly used measures of central tendency. These are the mean, median, and mode. In this section, or in this topic, we shall discuss how to compute the value and some of the properties of the mean, median, and measure of central tendency. This refers to a statistical measure to determine a single score that defines the center of a distribution. The goal of central tendency is to find a single score that is most typical or most representative of the entire group. And we have mean, median, mode as our measures of central tendency. Then we have mean, which is the most commonly used measure of the center of data, and it is also referred to as the arithmetic average of the scores. Most widely used measure of central tendency, used when data do not have outliers or extreme values. So this is a very important thing to always remember in using mean as a measure of central tendency. Make sure that the observations do not have extreme values. The computation of population mean, you have this symbol mu. Then all you have to do is take the sum of the scores, then divided by the number of observations. Here, the mu, this symbol, indicates that you're talking about population mean. Then, for the sample mean, you have the same process. You have to add the observations, then you have to divide it by the number of observations. This X bar indicates that you are getting the mean of the sample. Then for the mean for ungrouped data, so you still have to use the X bar. Then for the mean for grouped data, X bar, but in here, you have to multiply the frequency count and the observation divided by the number of observations. Now, let's have this illustration. Scores of 15 students in Mathematics 1 quiz consist of 25 items. The highest score is 25 and the lowest score is 10. Here are the scores. Now find the mean in the following scores. So all we have to do is take the sum of the test scores, then divide it by 15. So we got here 15.2. 15.2. So our analysis states that the average performance of 15 students who participated in a mathematics quiz consisting of 25 items is 15.2. The implication of this is that the student who got score below 15.2 did not perform well in the said examination. Students who got score higher than 15.2 performed well in the examination compared to the performance of the whole class. Another illustration here, find the grade point average GPA of student A for the first semester of the school year 2018-2019. Use the table below. Here, we have the subject, the first column, then the ratings in the second column, then the units earned in the third column. Then we have the product of the grades or ratings, product of the ratings and the units earned. So that's in the fourth column. So we take the product of the ratings and the units earned. Then we take the sum which is equal to 32. So in our solution, we have the mean is the summation of the product of the ratings and the units earned divided by the units earned. So we have here 32 over 26. So we got what? 1.23. So this means that the grade point average of student A for the first semester of school year 2018-2019 is 1.23. Mean for group data. So group data are the data or scores that are arranged in a frequency distribution. Frequency distribution is the arrangement of scores according to category of classes including the frequency. Frequency is the number of observations falling in a category. For this particular lesson, we shall discuss only one formula in solving the mean for group data, which is called midpoint method. The formula is this one. The mean is equal to the summation of the frequency times the class marks divided by n, or the number of observation. Here where x bar is the mean value, f frequency in its class or category, then x sub m is the midpoint of each class or category, then the summation of f times x sub m. So you have summation of the product of f times x sub n, or the class mark. Steps of solving mean for group data. First, find the midpoint or class marks of each class or category using the formula lower limit plus upper limit divided by 2. Then multiply the frequency and the corresponding class mark. Then find the sum of the results in step 2. Solve the mean using the formula x bar equals the summation of f times x sub n over n. Here we have an illustration. Scores of 40 students in a science class consist of 60 items and they are tabulated below. Here we have, okay, for the mean, so our frequency for the first category, 10 to 14, the frequency is 5. The class mark is 12. So 5 times 12, that is 60. So you just continue the process. Then we added the product. We have 1,345 divided by the number of frequencies, that is 40. So we get 33.63. Our analysis here says that the mean performance of 40 students in science quiz is 33.63, which showed that the students did not perform well in the said examination, while those students who got scores above 3.63 perform well. Okay, let's have the properties of the mean. First, it measures stability. Mean is the most stable among other measures of central tendency because every score contributes to the value of the mean. That is true because we have to add all the observations, then we have to divide the sum by the number of observations. So this is true. The mean of a finite collection always exists and is unique. So that is also very true because in a finite collection, the the mean always exists and it is unique. It is not repeating. It is all different at all times. Then it is easily affected by extreme values. So mean is not a good measure of central tendency if there are outliers. It may not be an actual score in the distribution. Okay, this means that sometimes we get a mean that is not among the observations. It can be applied to interval level of measurement. Interval level of measurement. Then it applies to numeric variables for it to be interpretable. So we cannot apply mean to qualitative data like the nominal data and the ordinal data. So mean is applicable to numeric variables. So we can have an interpretation for that. It is very easy to compute. Yes, that is because you simply take the sum of all the observation and divide it by the number of observation. When to use the mean? Sampling stability is desired. That's the first reason. The second, other measures are to be computed, such as standard deviation and coefficient of variation and skewness. Okay. When you compute for the mean of a given data set, uh, most often the standard deviation is included because the measure of centeredness is being used as as a point of reference and the standard deviation is used to determine how scattered or the spread of the distribution of the observation. Okay, here we have an illustration about the property that mean is applicable for numeric variables for it to become interpretable. Now, suppose you ask 5 of your friends about their favorite color given the following. 1, yellow. 2, pink. 3, blue. 4, green. 5, red. Now, if the observed values are yellow, pink, blue, and green, then you would have 1, 2, 2, 4, and 4. Getting the mean, we have 2.6. What does this value imply? Okay, so there's nothing we can say about the value 2.6. It's so hard or we cannot explain what this mean value stands for. So this is a proof that mean is applicable only for numeric variables. Now, effect of an extreme value on the mean. So this is also one of the properties of the mean. Here we have an illustration. Suppose you have the following numbers 1, 2, 3, 4, 5, and 8. Computing for the mean, we get 3.8. Hence, the mean divides the given observations into two equal parts. So we have, again, we have our mean, which is 3.8. So that is between 3 and 4. Since the mean is between 3 and 4, we see that 3 of the observations are to the left of the mean. These are 1, 2, and 3. And the other 3 of the observations, 4, 5, and 8, are to the right of the mean. So, the mean is not affected by an extreme value. Let's have the second illustration. Suppose you have 1, 2, 3, 4, 5, and 15. Calculating for the mean, we get 6. However, the mean does not divide the observations into two equal distributions. In fact, 5 observations are on the left of 6. Only one observation is at the right of 6. So the observations 1, 2, 3, 4, and 5 are to the left of the mean 6, while 15 is the only observation at the right of the mean 6. So in this case, the extreme value really affects the mean. Okay, let's come now to the second measure of central tendency, which is the median. Median is about sorting the observations into two equal parts. What the concern of this measure of central tendency is about knowing how many are above or below the median. But we are sure that 50% are above the median and the other 50% are below the median. Median is the second type of measure of central tendency. Median is what divides the scores in the distribution into two equal parts. 50% lies below the median value and 50% lies above the median value. It is also known as the middle score or the 50th percentile. For classroom purposes, the first thing to do is to arrange the scores in proper order. That is to arrange the scores from the lowest score to highest score or highest score to the lowest score. When the number cases are odd, the median is a score that has the same number of scores below and above it. When the scores are even, the average of the two middlemost scores becomes the median. The difference between weighted mean and arithmetic mean. This is a very important concept to understand. In weighted mean, some data points contribute more weight than others, while in arithmetic mean, each data point contribute equally to the mean. Let's have an illustration. Suppose you have the following numbers 1, 3, 5, 7, and 10. If you want to get the average or the arithmetic mean, all you have to do is take the sum of the data points, then divide it by their number of observations. That is 1 plus 1 plus 3 plus 5 plus 7 plus 10 divided by 5. The sum of the observations is 26. Divided by 5, we get 5.2. So, this is the average or the arithmetic mean. Again, each of the observation, each of the observations has contributed to the average. Now, let's come to the second illustration. For instance, if statistics students are given ratings based on their midterm and final ratings, suppose that 1/3 will be taken from the midterm examination and 2/3 from the final examination. If a student got only 90 in the midterm examination and 80 in the final examination, the rating would be, so 90 times 1/3, because only 1/3 of the midterm examination is to be included, and 2/3 of the final examination. So 2/3 of 80, we got 30 plus 53.33 equals 83.33. In here, we can say that the final examination rating has a greater contribution in the final rating of the student. So this is our illustration about weighted mean. Mean for ungrouped data. First, arrange the scores from lowest to highest or highest to lowest. Second, determine the middlemost score in a distribution if n is odd number and get the average of the two middlemost scores if n is an even number. Example, find the mean score of 7 students in an English class. So these are the scores. You have to take the mean by arranging the numbers. Now it is already arranged and the middlemost score is 15 because we have 7 scores here. So 15 is the median. So 3 of the scores, 16, 17, and 19 are above the mean. And the other 3 scores, 10, 5, and 2 are below the mean. Then another illustration, find the median score of 8 students in an English class. Here, we have 8 observations. So we have arranged the observations or the test scores. Then we see that 15 and 16 are the two middlemost scores. So we have to take their sum and divide it by 2. So you have 16 plus 15, that is 31 divided by 2, that is 15.5. So 15.5 is between 15 and 16. So the median here, which is 15.5, divides the observations into two equal parts. For the observations above the median, we have 16, 17, 19, and 30. And the scores below the median, we have 15, 10, 5, and 2. Okay. Effect of an extreme observation on the median. Suppose you have the following observations, 1, 2, 3, 4, and 5. What is the median? Of the given observations, 1, 2, 3, 4, and 5, the median is 3 because that is the middlemost observation. And these are already arranged, so our median is 3. It can be observed then that there are 2 observations in both sides of the median 3. And we can see that one on the number line. Suppose you have the following observations, 1, 2, 3, 4, and 50. What is the median? Since the number of observation is odd, the middlemost observation is the median. Hence, the median is 3. This median separates the observations into two equal parts. And we can see that one on the illustration that the median 3 has 2 observations in both sides. So, this goes to show that the median is not affected by extreme values. Median of group data. Now, the formula of getting the median of group data is this. This symbol for the median value equals L sub B, or that is the lower boundary, plus this bracket N over 2 minus CFP over FM times CI, where The symbol is the median value, MC, median class, category containing the n over 2, LB, that is the lower boundary of the median class. Then CFP, that is the cumulative frequency before the median class, if the scores are arranged from lowest to highest value. FM, frequency of the median class. CI, size of the class interval. Okay. Now, let's have the steps in solving median for group data. First step, complete the table up to the cumulative frequency. Then, get n over 2 of the scores in the distribution so that you can identify median class. Then, determine the lower boundary, the cumulative frequency before the median class, the frequency of the median class, and the class interval. Then, solve the median using the formula. So, those are the steps in getting the median of group data. Now, let's have an example. We have here scores of 40 students in a science class consist of 60 items and they are tabulated below. The highest score is 54 and the lowest score is 10. Let's see the tabulation. So that's correct. The lowest score is 10. That is the lower limit of the first category. And 54, the high score, is the upper limit of the highest category. And we can see that our N is 40. So 40 divided by 2, that is 20. Then the category containing n over 2 is 35 to 39. So 35 to 39. That is the category containing n over 2. Because in n over 2, the cumulative frequency before the median class is 26. So 20 is less than 26. So the median class is 35 to 39. Then the lower limit of the median class is 35. Then the lower boundary. So remember, getting the lower boundary, you have to subtract the lower limit by 0.5. Since the lower limit is 35, so subtract this by 0.5, you get the lower boundary, which is 34.5. So the cumulative frequency before the median class is 17. It's right here. Then the frequency of the median class is 9. Look at the header, F frequency. So you can use now and then the class interval, which is 5. Then you can use the formula. Okay? So all you have to do, you have to substitute the lower boundary by 34.5 and by 40, then CFP by 17, FM by 9, and CI by 5. Okay? So all you have to do is substitute. Then do the calculation. So you have here, this is 20 because n is 40 divided by 2, that is 20. So 20 minus 17, that is 3. Our cumulative frequency of the median class is 9. So you have 3 over 9 times 5. Then 34.5. Then you will get 34.5 plus 15 over 9 because 3 times 5, that is 15. Then 34.5 plus 1.67 because 15 divided by 9 is 1.67. Then add these two, you get the median value, which is 36.17. So our analysis here, says that the median value is 36.17, which means that 50% or 20 scores are less than 36.16. And it could be also said that the other 50 are higher than 36.17. Now, interpretation of the median. At least half of the observation are less than or equal to the median. Now, we have here are less than. This happens if the number of observations is even. But if the number of observations is odd, so this one, less than or equal to, less than or equal to, or at least half of the observation are greater than or equal to the mean. This general interpretation can handle all types of data sets, including those with tied values in the middle of the array. Now, properties of the median. The first one, it is a positional measure. Of course, it is because it certainly divides the observations into two equal parts. It may not be an actual observation in the data set. This happens when the number of observations is even. It can be applied in ordinal level. It is not affected by extreme values because median is a positional measure. When to use the median? The exact midpoint of the score distribution is desired. There are extreme scores in the distribution. So, in a given set of observations or data points, if it is very obvious that there is extreme value or there are extreme values, you have to use median. Now, let's come to the mode. Mode is the third measure of central tendency. The mode or the modal score is a score or scores that occurred most in the distribution. It is classified as unimodal, bimodal, and trimodal and multimodal. Unimodal is a distribution of scores that consist of only one mode. Bimodal is a distribution of scores that consist of two modes. Trimodal is a distribution of scores that consist of three modes, or multimodal is a distribution of scores that consist of more than two modes. Illustration. The following observations are waistlines in inches of 12 males. So 25, 26, 29, 30, 30, 29, 30, 30, 30, 31, 34, 36. Now we can see that there is a single mode, or there's a unimodal here, because 30 appears 5 times. So this is a unimodal. Then, a statistics exam scores for 20 students are as follows. Now, you can see that 72 appears 5 times, or the frequency count of the test score 72 is 5 and no other. Okay, so 72 is the mode of the test scores of 20 students. So this is also unimodal. What about this one? Let A equals the set containing the numbers 1, 3, 3, 3, 4, 4, 6, 6, 6, 9. So we can see that there are two numbers in the set which have the same counts. You have 3, it has 3 counts. 6 has also 3 counts. So we can say that this set A has two modes by modal. Now, another illustration, scores of 10 students of Section A, Section B, and Section C. Look at this. Then, the score that appeared most in Section A is 20. What is the count? 20 has a frequency count of 3. There is only one mode. Therefore, score distribution is called unimodal for Section A. The modes of Section B are 18 and 24. 24 has a frequency count of 2. 18 has also a frequency count of 2. So, Section B has a bimodal distribution. Then Section C, it has 18 with 3 counts, 21 with 3 counts, 25 with 3 counts. So there are 3 modes for Section C. Therefore, it is called a trimodal or multimodal distribution. Mode for group data. In solving the mode value using group data, use the formula, this symbol, the symbol for mode equals LB, that's the lower boundary, plus the quantity D sub 1 over D sub 2 plus D sub 1 times CI, where LB, that is the lower boundary of the modal class, MC modal class is a category containing the highest frequency, D sub 1, difference between the frequency of the modal class and the frequency above it when the scores are arranged from lowest to highest. D sub 2, difference between the frequency of the modal class and the frequency below it when the scores are arranged from lowest to highest. Then CI, that is the size of the class interval. Now, illustration. Scores of 40 students in a science class consist of 60 items and they are tabulated below. What is the mode? Here, we have the first column, that's the score intervals. Then the second column, that's the frequency. So first, we have to determine the modal class. The modal class is 35 to 39. Why is this the modal class? That is because in this interval, we have a frequency count of 9. So 9 of the test scores fall in this category. So that's why 35 to 39 is our modal class. Then the lower limit of the modal class, that is 35. Then the lower boundary of the modal class, knowing that the lower limit is 35, so the lower boundary is 34.5. Then D sub 1. D sub 1, this is the difference of the frequency of the modal class and the frequency below it. Then D sub 2, that is the frequency of the modal class minus the frequency above it. Then the class interval is 5. So, after having known the necessary information and data, we can use now the formula. So, all we have to do is plug in. For lower boundary, we have 34.5. For D sub 1, that is 7. D sub 1 is 7. D sub 2 is 3. Then the class interval is 5. So you have this 7 plus 3, that is 10. Then 7 times 5, that is 35. Then 35 divided by 10, that is 3.5, plus 34.5. So that is equal to 38. So the mode of the group data is 38. The mode of the score distribution that consists of 40 students is 38 because 38 occurred several times. In the properties of the mode, it can be used when the data are qualitative as well as quantitative. Take note, mode can be used in qualitative and quantitative data. It is the easiest to interpret among measures of central tendency. It is not affected by extreme values. It may not be unique since not all the time the mode is unimodal. That's true. Sometimes it's bimodal. The distribution is bimodal, and sometimes also it is multimodal. One advantage of the mode is that it can be applied to observations that are measured in the nominal level. Just like, for example, the illustrations we use in this learning material about the choosing of favorite colors. That's nominal data. So you could determine the mode or the color that is the most favorite among the people you ask about it. Then it may not exist. That's true because sometimes our data does our data do not have this mode because the frequency counts of the observations is not equal. When to use the mode? When the typical value is desired, when the data set is measured on a nominal scale. That would be all. Thank you very much.